Hello students, welcome back to OrganiChemVerse. In this video, let's solve a tricky question based on the reducing reagents and also the stereochemistry of the reactions. What exactly it means is that there are different reducing reagents and there are different functional groups in the molecule. Based on what is the reactivity of the reducing reagents, you are going to get different products. And you can see that there are chiral carbons in the molecule, or upon reduction, you are going to get chiral carbons. Considering all these points, you need to choose the correct statement or statements from the given options. Before we start solving the question, first let's analyze what is this molecule. This is a bicyclic compound and it is called as Norbornyl compound. Such bicyclic compounds which are 7-membered, we call them as Norbornyl compound. It is having ketone as one of the functional groups here, and there is a carbon-carbon double bond. And what is this? It's an ester. How ester? Look at this, COOMe. So it's a methyl ester. Here also we have an ester, but this time the oxygen is attached to this carbon, and here we have a pH, that is nothing but phenyl. Remember, this phenyl you can elaborate like this. Phenyl refers to C6H5 group. So there is an aromatic ring in the molecule. Don't forget about that. First, before we start solving this question, let's understand how many chiral carbons are there in the molecule. Now, is this a chiral carbon? Yes, because it is attached to a double bond carbon, a carbon which is in turn attached to an ester and ketone, and of course there will be a hydrogen. So this is a chiral carbon. What about here? Here also we have a chiral carbon, and so does this carbon. This is also chiral. Why so? Oxygen, carbon, and here we have a tertiary carbon. So this is also chiral. So is this. Okay. 1, 2, 3, 4. These are the 4 chiral carbons already present in the molecule. What about this one? So this is a ketone. That means the carbon here is sp2 hybridized. Hence, this cannot be a chiral carbon. Same with these two carbons. So once you understand all this, let's analyze the reagents given. What is the function of sodium borohydride? Sodium borohydride can reduce aldehydes and ketones. Aldehydes to primary alcohol, ketones to secondary alcohol, but not the esters, not carboxylic acid, not even carbon-carbon double bond. Let's take over the lithium aluminum hydride. This is a strong reducing reagent which can reduce aldehydes, ketones, acids, esters, nitro compounds, nitriles, etc. But will it reduce carbon-carbon double bond? No, it will not reduce an isolated carbon-carbon double bond like this. Now, what about hydrogen platinum? So you can call this as a catalytic reduction, wherein it can reduce carbon-carbon double bond, right? Also triple bond, and it also reduces aldehydes, ketones, but not carboxylic acid, but it will reduce the ester. So with this much information, you can pause the video and try to solve this question on your own. If you're not able to solve, don't worry. I'm here to explain to you how this question can be solved and you can choose the correct answer. So let's get started. Let's first find out what our products PQ are, and then we can look at the stereochemistry. That means what kind of products are going to be formed, enantiomers, diastereomers, or mixture of products, etc. See, when this is treated with sodium borohydride, since it is a reducing reagent which reduces only ketone from the given molecule, you are going to get an alcohol. So what alcohol are we going to get? A secondary alcohol. And what about the ester? That will remain as it is. So we can write down the structure of the molecule like this. Now, what about the stereochemistry of this molecule? See, the hydride can attack the carbonyl carbon either from this side of the plane or from this side of the plane. Say if it attacks from this side, if we are getting R configured molecule, right? If it is attacking from the other side, we are going to get S configured. That means what? We are going to get two products as it is generating a chiral carbon. So here is the chiral carbon. So it will be generating mixture of products. What sort of mixture of products? See, already there are two chiral carbons here and chiral carbons over here. Say, let's assume they all have same configuration. Okay, it differs only at this particular configuration. All these four carbons will have same configuration. Differing at only one configuration means what? It's going to form non-superimposable non-mirror image. So from sodium borohydride reduction, we are going to get diastereomers. Now let's check for second reaction, that is with the lithium aluminum hydride. It will not reduce the double bond. Remember that carbon-carbon double bond will remain as it is. What about the ketone? Of course it will reduce, and you can see the chiral carbon is generated over here, right, because of the hydride. Exactly like this, because lithium aluminum hydride also generates hydride ions, right? Therefore you are going to get both R and S configured over here. And now there is an ester. First it will cleave the bond here, right here, and then we get an aldehyde. Aldehyde further will get reduced. Therefore you are going to get CH2OH, nothing but a primary alcohol. Whenever an ester undergo complete reduction, you are going to get a primary alcohol. What about here? The bond will get cleaved here and we are going to get OH. And what sort of alcohol is this? This is a secondary alcohol. Primary, secondary, and what is this? This is also secondary. Remember, whenever we reduce esters, aldehydes, ketones, we are going to get either primary or secondary alcohol. Only with the Grignard reagent and ketone, we are going to get a tertiary alcohol. Remember that. Now, let's look at the last part of the reduction, hydrogen platinum catalytic reduction. Of course it will reduce the carbon carbon double bond and also the ketone, right? Here also we are going to get a chiral carbon, right? What about here? The ester will get reduced exactly like this, and here also same like this. So what is the difference between this and this molecule? The double bond. The rest everything is same, just the double bond is gone. And what is this? A secondary alcohol. This is primary alcohol and this is also a secondary alcohol. Okay, so what are the products? PQR. This is P, this is Q, and this is R. Let's verify the options. Product mixture B contains two diastereomers. Yes, that is true. We have already established it. So option A is correct. Product mixture R contains two diastereomers. Let's see here. See here exactly how it happened, right? You are going to get two configured. What about the carbon here? See, the reaction is not taking place over here. When the reaction happens here, right? This chiral carbon, whatever is there, it will remain as it is. R will remain as R because the reaction is taking place at this carbon. Same here also, it's happening here. What about the configuration here? Will remain same, but only on this carbon it's going to be changed. Obviously you are going to get two diastereomers, therefore this is also correct. For option C, one of the products from product mixture Q, so this is our Q, contains primary, secondary and tertiary alcoholic groups. So we have primary, secondary, but not tertiary. So as I told you earlier, the tertiary is possible when ketones, esters react with Grignard reagent, not with the reducing reagents like this, because all of them do provide hydrogens. That means what? You are going to get either primary or secondary, not tertiary. Now the last option, one of the products from product mixture Q, right, on treatment with PCC gives aromatic aldehyde. See, I have written only one product, right? What is the other product? So here, when this bond gets cleaved, right, here you are going to get PHCOH, which upon further reduction, because it is complete reduction, right, it's going to form an alcohol. What alcohol? A benzyl alcohol, like this, right? So this will be our one of the products in mixture, right? But the question is, when that product upon PCC gives the aromatic aldehyde, that means what? See, this is reduction. When we do oxidation using PCC, right, again we will get back the aldehyde. So this is also true. So among the given options, A, B and D are correct. So students, whenever such complex questions are given, break it down into different parts, solve it one after the other, and then choose the correct options. I have given one more question at the end of this video. Please do solve and comment your answer. And if you still have any queries on this question or any other question, feel free to comment your queries. And don't forget to subscribe the channel. Thank you.